All right, so well, this is kind of different. Signal sequence models from a signal processing perspective. My background is signal processing, but I'm really interested in machine learning, as is pretty much everybody these days. And so, like everybody here, presumably, I want to understand it better. I want to understand how it works. And so, for me, that means turning it into a filter. There's a signal processing wizard who once said, when you think about it, everything's a filter. And so I'm here to make that case for machine learning and to just kind of approach it that way. And I think it's kind of nice. And you also see it coming up, like many of you have probably seen structured state space models. That's signal processing leaking into the story. So it's kind of motivated along those lines. And so let's just see. So my background, I started out as a musician, got into math and physics in high school, and then majored in double E in college, where I loaded up on control courses and signal processing. Digital signal processing was just emerging at that time. And then for my graduate studies, I was mostly doing system identification, which is extremely relevant to machine learning, especially differentiable DSP, if you follow that stuff, because that's basically what it is, differentiable systems embedded in neural nets. And neural nets themselves are, basically FIR filters with a nonlinearity that you can differentiate through. And so I was doing this stuff at the Stanford AI Lab, where one room was devoted to music, and that was the Center for Computer Research in Music and Acoustics. John Chowning was the founding director. And so I started out there as a volunteer and ended up in the graduate program. And so I was basically doing things like this, taking a really great tube amp and then bringing it into a digital form. So it's all about capturing all the equipment in my garage or studio and turning it into racks of, well, just, fast code. Nowadays, you can do everything in an iPhone. And so, I still play normal instruments, but they're usually now controllers that control digital stuff. So that's just where I'm coming from. And so I don't actually really need machine learning that much, except there is a lot of neural signal processing going on. Look at something like Neural Note. It's a DSP, a VST plugin that or any kind of plugin, really. It's a juice plugin that you can then, use for polyphonic transcription of tonal music. So there's a lot of really good stuff. And that's just one example. I just happened to talk over in class. So my classes are devoted to spectrum analysis, filter analysis, and structures, and both of these are relevant. So the spectrum analysis is where you really get into the inner product. So understanding projection, and that's really a big thing to understand, I believe, in machine learning. And then the filter structures lead to things like structured state space. So really both of these, basic courses, these start at the high school level. That's because, I'm teaching in the music department. I've got to be able to handle everyone. And so these are actual links that will go to the pages and have all the books. That might not, oh, yeah, okay. I thought I might have just one thing shared. And so you can actually go find all this stuff. And then I have more advanced courses on physical audio signal processing and time frequency, which is both basically about, computational models of musical instruments. So the physical models are more expressive. And this is DDSP ready. DDSP is beautiful for, calibrating these models to examples and so on. There's a lot of projects along those lines. And then, of course, it matters how you hear. So you only want to, optimize your models to the extent that you can hear the difference. And so perceptual audio coding is a big topic related to this. And your ear is a time frequency signal processor. And so we use that all the time. And it's really used heavily in machine learning. So your adversarial losses in audio are very heavily based on this kind of audio signal processing, perceptual audio signal processing. So it's all very, very relevant. In fact, one guy in machine learning, I was having this discussion with him. He said, "Oh, it's all signal processing. So everything's a filter, and it's all signal processing." And my textbooks are free online. I want to recommend those if you don't have the necessary prereqs and you want to, pick up, a very easygoing tutorial on, inner products and projection. Geometric signal theory is one way it's described. Then this is that book, and it's just free online. And then the filters as well. That's all here. And so and then the more advanced books are here. And then in machine learning, I'm just compiling reading lists. So you can go into these and see what we've been talking about. The audio codec section is pretty nice. It's just PDF. So, there's nothing really original here except maybe a few comments and so on. And so that's that's the setting. That's the background. That's where I'm coming from. And
Hey,
so,
Julius,
yeah,
can I ask a quick question?
yeah.
Could you kind of briefly describe DDSP? I think I can infer what it is, but could you describe that quickly?
Yeah, it's differentiable signal processing. So I it came up in the context of sound synthesis using additive synthesis, so science plus noise. And so let me just take you right to the right place. It's the Google Magenta project. So I just typed in DDSP and I got the first link as magenta.tensorflow.org. And so here's the nice homepage. Jesse Engel was the first author on this paper. And so here's, you've got your GitHub code, really nicely done, audio examples, collab, just really, really nice. And so the basic idea is you're using a neural net to fit the, oh, good, we have the architecture here. So here's your audio. And so you want to encode that in such a way that you can resynthesize. So what we're doing is we're synthesizing audio of the same type with various transformations. And so we're going to use additive synthesis, which nowadays is science plus noise. Well, it's probably a lot of different things, but the state of the art, in my opinion, is science plus noise synthesis. And here are the signs. Here's the noise. So the sinusoidal expansion gets you all your harmonic sounds and tonal sorts of sounds. But if you've got noise components, you can do it with sine waves, thanks to Fourier's theorem. But that's a very inefficient modeling thing. So filtered noise plus sinusoids gives you a much more efficient modeling set for audio. And so we're just trying to find the envelopes of the sinusoidal components, the envelopes of the filtered noise, and the filters themselves in using good old machine learning, MLPs and such. And so the encoder, well, first of all, I think this is really a good example of great practice, still today. You separately extract pitch, and there was a separate neural net for that called CREPE, CREPE from NYU, and it's a really nice F0 estimator. Yeah, I heard some noise. So that's a nice F0 estimator, and so you just get that right. And you also separately measure the loudness, which is very simple. It's just an RMS, dB, RMS kind of thing. So you've got your pitch and loudness factored out. And so that only leaves timbre. So timbre is defined as everything about a sound except for the pitch and the loudness. And so the Z vector is your timbre vector. And so you're encoding whatever the sound is, with its pitch and its loudness modded out, you're encoding its timbre here. And then you're learning how to decode that in the form of amplitude envelopes and filter envelopes for additive sense plus noise synthesis. And he's also got some reverb here, which makes it nicer, and that can also be learned. And you create the audio. So that'll kind of give you your space, your air around it all. And so, yeah.
Yeah, so Julius, so it sounds, so if it's differentiable with respect to something. So is there a loss function? Is this kind of like an auto encoder that I might think of in neural nets?
Yeah, there's a multi-scale loss function, which you see in all the audio codecs. The adversarial loss, even the reconstruction loss, I think, is multi-scale spectrogram based. And that's because audio is that way. The ear is a multi-scale spectrogram encoder for the brain. It just encodes into the auditory nerve.
Gotcha. Okay, thank you.
And you do have to differentiate. You have to differentiate that whole thing, and the gradient has to propagate back through your structure. So your sinusoidal oscillators and your filters, and then into your neural net. So the decoder and the encoder have your. I think we probably have. Well, if I pull the paper, we can get into the architecture here. It's basically MLPs, and I think male frequency capsule coefficients are used, and so it's pretty straight ahead signal processing, neural nets, deep learning type stuff. This goes back to 2017, I think. It's pre-transformer.
Very good, thank you.
So Julius, would it be accurate to say that DDSP is using neural nets with DSP?
Absolutely, yeah. So I think the basic idea that Jesse had and whoever else he was talking to was, we know how we want to do this. We want to synthesize audio, and we can do anything with a neural net. We have universal approximation, et cetera, but we would like to have some knobs that we like, right? And this is something sound designers say as well. you know, they want to be able to tweak the same old knobs they've always tweaked. So instead of just getting the audio like something like Udio does or Suno, let's, you know, just calibrate our synthesizers or our EQ sections or our sound design tools. Just give us the settings for our normal tools so that we get a great preset that sounds fantastic and we can just leave it alone, or we can go in and we can tweak it the way we always do. We have all the usual tweak knobs available to us because we understand the representation. So we're taking part of the neural net, which is a black box, and making it a white box, our familiar, good old friendly, you know, interfaces. And so that's why you have to improve structure. I heard Anna Huang describe it as structural priors. So we would like structural priors in our network that will do something we like, that we understand, that we recognize, but it's got to be differentiable. You know, it's got to have the same good properties of MLPs, you know, weights and biases and smooth activation functions. So that's really straightforward until you get to the optimization. So you really still have to be careful that your optimization is as quasi-convex and robust and well-behaved as these neural nets are. You know, the neural nets are, I would say, surprisingly optimizable for a nonlinear optimization. I think it was a big surprise to anyone with experience in nonlinear optimization how well they could optimize something that big. And so you still have to keep that. So you want to judiciously choose your DSP structures to be not only differentiable, but differentiable without lots of little spikes in the loss function. You want this loss function to look like a bowl, right? Ideally, it looks like a nice quadratic bowl because you want gradient descent to be able to get down to the optimal setting. So that's where the art of it is. The art of it is, you know, choosing your models to be optimizable. And there are a lot of ways to do that. And we have actual research on that, you know, because that goes back to optimization of models. And we have actually dissertations in that area at Karma, for example. Huiling Liu comes to mind. She was a EE PhD student who I think came up with the first idea that I know of, the optimization proxies, where you're able to optimize something that's easy to optimize, and then it has a known translation to what you really want to tweak. So you just do that transformation. Now you got the knobs you like that have the more robust behavior. So there's tricks like that that have been established before, you know, all this stuff took off. So that's why we need a lot of talking and diffusion, right? We need to, you know, talk to each other and, you know, you see signal processing ideas diffusing into machine learning, and you see machine learning diffusing and in fact dominating signal processing. So it's kind of a two-way thing, and it's fun to be a part of that.
Julius, have you seen that concept translated into like image generation or something like that?
I have not. I have not been active in images. Image processing, I've tracked it well enough to know just, you know, what they do. You know, like the GPT came from there and so on. But I've never been active in image signal processing personally.
Okay.
Yeah, so that either it's low-hanging fruit or it's been done, and we just have to find the paper. And
More likely.
yeah, more and more the paper's out there somewhere. It's just so quick. That's why I'm really excited about all these tools for you know, taking my thousands of PDFs and putting them in a RAG system, and I can just ask, you know, I can just say to the LLM, you know, did anyone do this in the last 10 years or whatever? And so pretty soon we're going to be able to navigate the literature a lot better than we can right now. Right now, it's really hard to keep up with it all. Roger has a hand up. Is that?
Oh, sorry. I that was from prior. I'll bring it down. Thanks.
Any more questions, discussion? This is a cool topic. I could actually talk. I can make a separate talk on DDSP, although that should be just. I mean, it's so well established. It's not a new cutting edge thing anymore, but there's a lot of follow on. I mean, there's a huge amount of. I would say at the DAFX conference, that's the Digital Audio Effects Conference. I'd say that's my #1 conference. I would say there's like 5 papers on DDSP type stuff every year. So it's a big sub genre.
Do you see a merging though of machine learning techniques into signal process, you know, into the audio signal processing, I guess is what you're talking about?
Well, we're picking and choosing from it. it's too powerful to ignore, but it's also too expensive to really do, but we do a certain amount of it. So that plugin I mentioned, Neural Note, it has a real-time inference neural engine called RT Neural. That's by Jatin Chowdhury, and it's very high-speed C++ implementation, and it's supposed to be better overall than some of the like TensorFlow Lite, and there's a PyTorch there's a Lite PyTorch as well that are intended for real-time or deployment in a high-speed situation. So RT Neural is what it uses, and we know Jutin, and so but it's still very expensive, and your net is going to be pretty small. Another one is Rave, and Rave 2 is the big one now, RAVE. It's more of like a principal components approach. It's not like a full-blown MLP kind of thing, but that runs in real time, and it's used extensively for real time. So you learn a bunch of interesting basis signals, let's say, and then in real time you can morph among them. So you get really higher level intelligent morphs that are much more interesting structural morphs, which you've seen in images, of course. I mean, that's the whole thing. Like, it really got amazing with diffusion, where as you morph from one face to another, you don't go through some smear in the middle. You go through plausible faces all the way along. I guess GAN started that, right? And where you had real adversarial losses, and you keep things in distribution the whole way. That's the trick.
Right.
You don't just crossfade, right? So that stuff's really, really fun and better. And DDSP was concerned with that. So that was, Morse was a principal application of the original DDSP, actually. And they were kind of, morphing in this Z domain. So you have this, put a joystick, I don't remember how many dimensions this was, but let's say it's 100 dimensions. So what you really want, so it opens up this whole new field of 100 dimensional controllers. How do you fly around in 100 dimensional space? And so, we have a bunch of ideas. A lot of people have ideas, so maybe you control a subset of 3, and then your left hand will select which 3 dimensions you're in. And maybe you have a wheel that will very quickly, scan through the space, or maybe take a random selection. So a lot of interesting things to explore. But of course, as we know, not all the dimensions make a lot of sense. So you really want to identify the ones that are really nice, the gender dimension in Word to Vec, or there are all these directions in the latent space that mean something, but it tends to be a small number that we really know about, right?
Yeah, you're talking about the ones that would have any value in your particular type of mixing. Is that what you would be doing?
Yeah, we want to
okay.
morph along a known dimension, such as a size dimension, or between among cats, let's say, from tiger to lion to house cat, that kind of stuff. Those are the things I've actually seen done. And so, and I've seen research that will actually constrain the latent space to have labels that are known. And that was at Georgia Tech. I think Pati, P-A-T-I, was the last name on that one. And he could, as I recall, he could get about 3 dimensions that were enforced labeling, where you knew what they were before you would start to lose model capacity. So if you go too many, then you can get those labels, but your model capacity degrades, and so there's that trade-off.
Interesting.
Julius,
Thanks.
When you talked about like a gender dimension in image, for instance, what would be the types of directions that you would have in this audio, whatever I call this, codec, whatever it is?
Well, anything that a sound designer wants. So most of my research has to do with physical instruments like guitars. And so I would like to be able to morph from one guitar to another. And so, the pickups might smoothly transition from one spacing to another. The strings might, very smoothly just get thicker and more stiff, and that gives them a very different sound. And if the pickups have to move apart and a new one moves in, that just has to kind of appear gracefully. Single coil becomes double coil. So you just want these graceful transformations that are, that are hopefully audibly recognizable. You'd like to be able to say, as you move along that line, that you can hear the transformation. And another really good example is voice. Like if you're morphing from let's say a male voice to a child voice, then the formants are going to shift. The resonances of the vocal tract. So the child has much more spread out resonances because it's a shorter vocal tract, and so the morph should move the formants as resonances, as opposed to just like fading out one set of resonances and fading in the new set of ref. So the really obvious thing is just crossfade, right? So you'll fade out the old resonance and then the new resonance will fade in. That doesn't sound like anything. It just sounds like, so you go from one thing to a superposition of things to one thing. But can we get it to just really do all the right things in between? So that's an old classic. And physical modeling takes care of that. So your structural priors will give you that automatically if you have a physical model. And that's one of the reasons physical models are so popular, is that they're popular among people who want this, because you have that structural constraint. It can't do anything beyond what the model can do, and so it's one way to stay in distribution. The model can't go out of distribution. It has to be that kind of model, and so you get it automatically. You don't have to train for it.
So do you just kind of probe for these directions, or is there some sort of guidance that you use when you're training them?
Well, in the model case, it's just going to happen. But in the more general neural net case, yeah, you gotta probe. And I don't have personal experience in that area. I mean, I've thought about it. I think it's an interesting topic. We even had a little bit of a Slack discussion on that, where the idea was you can just find them. So you embed a token, and then you embed a token that's related, but for an increment on this dimension we're interested in, and then you subtract them and you get a vector that's hopefully in the direction. The difference vector should be in the direction of that that trait, if it's in there, if it's been trained into the embedding. And so I don't really know much about this, but I imagine that's how they figured out king minus man plus woman equals queen, that sort of property, the word to vec stuff. So I don't know how they do that. How do they do you know how they do that? Or and maybe Anthropic's doing this kind of stuff. I don't know that much about what's going on at Anthropic for mechanistic interpretability, but I imagine there's a lot of that kind of thing going on there, to try to read out what's going on in there, what the dimensions are, the dimensions of control. I'm sure it's going on like crazy, right? I mean, we just need to dedicate a week to getting PDFs on that topic and catch up. So yeah, but I don't have personal experience yet, and I don't need it because I've got models. I'm a model based guy, so I'm set, right? I don't have this problem. You were going to say?
Yeah, I'm done. Thank you.
Okay. Yeah. No, it's very interesting, and I'm definitely interested on behalf of other people. But I definitely have decades invested in building the right models, and so I just want to calibrate them. And I'll provide the in distribution path among settings. And my only real problem is, making everything convex enough to train well and really not get stuck. And you find that a lot in audio because there's so much oscillation. Oscillations are notoriously non-convex. If you need to change the frequency of some oscillator or filter resonance, then you have a very non-convex optimization on your hands. And it's well known, well understood. So you have to really kind of solve that and then install it in the DDSP training in that way that is going to work. And that's where optimization proxies are very nice. So this is great. I know now I feel like I'm going to have enough material. At this pace, we'll be okay.
Well, Julian,
that much.
We told you.
Yeah. We can take any subject and stretch it to an hour and a half to 2 hours.
Excellent.
I mean, so don't worry about it. And the deal is, you know how this works, right? If you go long and you need to go to next week, we'll go to next week.
Okay. Sometimes.
So don't feel that we're your time boxed or anything like that.
Okay, great. Yeah, I think the discussion's more important than anything, at least, especially to me, because I'm hoping that we can discuss some of these things. I have actual questions coming up here. So here's the idea. This idea started at the Karma Open House, which is just a few weeks ago, where I was going to give a talk, and how do I bring this to, you know, Karma students who are, you know, musicians and, you know, master's students who are not necessarily, they basically don't have one required signal processing class, and it's Music 320. And so my goal with this talk then, which is, you know, much bigger now, was to try to convince them that they might be able to really understand machine learning, you know, large language models and such, at least structurally, in terms of their one signal processing class, Music 320. So the conceptual assignment is do something cool with a one-pole recursive filter, and here it is. So here's our first actual signal processing. So x of n is the input sample, you know, so floating point number usually represents like the pressure at a microphone at one sampling instant, and you got like 44,000 samples per second at least. And then you go into a gain, and you go into a summer, and then your output, your filter output is here. And so this is the signal processing notation for a unit delay. And the reason for that is that the Z transform of a unit delay is this, Z inverse. And you don't have to know about Z transform, just know that this is a one sample delay. And then we multiply it by a feedback gain, P, and it's called P because that's where it puts the pole. So this is now a one pole filter with a pole at Z equals P. And if you do look at the transfer function, which is here, you can see that when Z equals P, the transfer function gain goes to infinity. And so that's why it's called a pole. It's a singularity in the transfer function. But we keep P less than 1. So P is never equal to 1 or greater. Well, it might be equal to 1, and then we get an integrator. And that's dangerous living, right? Because it just grows forever. So this is your basic one-pole filter. And so every 320 student knows about that. And here's the so-called difference equation. This is what you would implement in code, like C or C++ or Fortran or something. So your output at time n is the gain times the input at time n plus the feedback coefficient P times the previous output. And you start at time 0 with some initial condition for y of -1, and you just let it go for all time. And it will give you a nice low-pass filter if P is, you know, greater than 0 and less than 1. And so this is the transfer function. It's the Z transform of the output over the Z transform of the input. And this is what it turns out to be. Just think of it as taking the impulse response of this and turning it into a polynomial. It's kind of a polynomial generator approach. I don't know. Let's not worry about it. So the idea for the hypothetical brilliant 320 students said, I know what I'll do. I'll make an associative memory out of this. So the input can be a long vector. So we generalize our samples to vectors. And so we'll have some dimension capital N, and it can represent anything we want. It can be any label. So it's this, you know, it's a label processor now. And so let's make things simple. Let's just set the gain to 1. Let's set the pole at -1. And so we're just going to sum our input back. Actually, that should be P equals 1. Sorry. I was using official notation, and there's a sign flip when you change notation. I'll fix that. So you choose the dimension so large that the vectors are mostly orthogonal. We talked about this last week, that if you have a large dimensional space, then most vectors, if you just pick 2 random vectors, they're orthogonal with a high probability, you know, substantially orthogonal. And so we're going to now retrieve vectors in this memory using a matched inner product. So W is the vector we're looking for. We're saying, is that vector in the memory? And so W transpose X is the inner product of W and X. And 320 students see this all over the place because in 320, X is your input signal and W would be a particular sine wave. So it'd be samples of a sinusoidal you know, unit amplitude sine wave at a frequency. You're trying to measure, is this frequency present in the signal? And so it is if your inner product is greater than some threshold. And for us, these are just real numbers. And actually, I probably want a absolute value here, really, in principle. But let's just say that's not going to be a problem. But you're basically just looking for collinearity of the of the query. So I'll call W the query vector, and the actual signal. In this case, it's just some label. So you're actually looking for a specific coordinate pattern in the vector.
Hey,
and that's how you detect what's in the memory. Yeah.
W, what's the size of the vector then for Either.
They're both linked in, so they're both model dimension.
Oh. Okay.
So in the MLP world, it's a pointwise thing. So one point is one vector in the embedding space, in-dimensional embedding space. So we only need one perceptron to implement this.
Oh.
And that's the observation here is that, hey, we just wrote down a perceptron. If you learn W, but in this sort of invention mode here, we're just saying we know what we're looking for when we're looking for it. So we store our vectors as just a sum, and that makes it a vector memory, and we just rely on orthogonality to keep them all retrievable, and then we come along and retrieve them with inner products. And what's a nice property here is that the similar vectors, as long as closeness in Euclidean space is similarity, then if we retrieve something that's near X, then it might fire, but it's at least similar. So you get that nice property that, well, either we get what we're looking for or something similar to it, and maybe it's a synonym, maybe it's close enough. So you get that nice, associative memory property that you get from the output of word to vec, for example. And it also starts to maybe suggest perceptrons. So we're sort of like creeping in the direction of neurons simulation. Okay, so this is just talking a little bit more about vector retrieval by inner product. So you have some sum of vectors, and then you have a query vector. And this is just reminding people that, inner products are linear. So the dot product on the vector memory will distribute through the sum of what's in the memory. And so you'll get 0 for everything that's, orthogonal, and you'll get something substantial when you hit the vector that's in there, if it's there. And then that'll be the norm squared. And then you want that greater than your threshold. And so that's your bias in the neural net. And so you have this detection threshold, B of K, and it depends on the norm of the vector. So we just piled up all these vectors. We don't know anything about them. They're just random vectors that mean things. It's just a bunch of labels, but the norm matters. So in other words, our detection threshold is proportional to the norm squared. So that makes a suggestion that I think is being used, which is reserve the radial dimension for similarity scoring. In other words, we'll just start using RMS norm all over the place. RMS norm will set the norm squared to 1. And that means all of our biases are in the same units. That means, 0.01 means the same thing. And we can figure out what the threshold is for a random vector and just set it a little higher, and anything above that will be a detection, and we don't have to change it as a function of our input vector. It works for all of them. So that seems like a good thing to do, right? So that means then what we really want is embeddings on the hypersphere. And I don't know that that's really being done, but it's done pretty fast, because you don't have to go far into these, architectures nowadays to hit an RMS norm. But I did look, and word to vec is not explicitly normalized. It doesn't project onto the hypersphere during training. So that, to me, that's a suggestion. That's something that should be tried. I'm sure it is. I bet Google knows all about it. OpenAI knows all about it. Meta, probably everybody knows all about this, but I haven't seen it in print anywhere. Not yet anyway. But there, I'm sure there's another million PDFs I should read. So this is RMS norms. It's just,
Julius,
yeah.
quick question. When you say similarity relative to word to vec, what kind of similarity are you referring to? Because I mean, there are acoustic features, there are auditory features, there are articulatory features. What kind of similarity should this embedding on the hypersphere have?
All of the above. I mean, this is what we were talking about a little while ago. Ideally, your embedding, which is in dimensional space, where n is very, very large. Now that we're on the hypersphere, directions on the surface of the sphere, and I guess there's n minus 1 of them, capital N minus 1. So for the original transformer, capital N was 512. So that leaves us with 511 directions that we can take off in on the sphere. And we want all of those to mean something vital to us that really matter. And so, there could be the gender direction as in word to vec. There could be all kinds of articulation details. There's any quality you want. So you have 511 parameters to assign. Well, what you really do is you train them up and you try to figure out what they are. And if you have to, you influence the training to make them what you want. But as I was saying, you can lose modeling capacity if you over-constrain it. So anything, the answer is everything and anything.
Can I ask, has anybody studied whether if you normalize embedding vectors, they're, they still have the properties of distance similarity?
Well, I think they'll be at least a little bit similar because RMS norm is used so extensively. In other words, they get squashed to the sphere pretty fast. But I haven't seen anybody really, that's a great experiment. I'm going to add that to my list. I have a lot of little small experiments to do, and this would be a good one. Just, normalize the output of word to vec to unit norm and see how it does. And I predicted it works okay. Maybe not, it's probably going to degrade a little bit and not a lot. But if you had trained word to vec, if you retrain actually you can retrain word to vec. Yeah, you get the whole framework. You just train it with that projection onto the hypersphere and get one that comes out on the hypersphere out of the gate. And now when you go through RMS norm, you don't distort it. You don't distort the meaning metrics on the surface of the sphere.
Yeah, and you should also try that with WAV2Vec, because WAV2Vec 2 is a pretty good audio tokenizer. I believe it is what Google Gemini Pro 1.5 is using when you upload an audio file in AI Studio, Google AI Studio, to one of the Gemini models. It will tell you after it uploads the audio file how many tokens are in it, and that makes me think that they're using WAV2Vec 2. Do you say WAV2Vec or WAV2Vec when you pronounce
I would say wave, but yeah, WAV2Vec was more likely to get spelled right.
Yeah. Anyway, thank you so much.
Thank you. Yeah, I'm gonna check that out. I'm sure I've checked it out in the past, but I need to refresh my memory on that one. So
Jim, if I could make a quick comment on that subject. So
please.
if you think of your concepts, whether it be words or whatnot, as living in a vector space, okay, so then like perhaps tiny, small, medium, big, large, gigantic, like sort of live on the same vector, but with different magnitudes on the direction, right? So if you want to be able to express concepts like that as the same direction, but with different magnitudes, then they can't all live on the surface of the unit hypersphere. So you can say that like your concepts all live on, so like the concept of size can live on the unit hypersphere, but the individual expressions of small and big would not live on the surface, if that makes sense.
Hey, Ted, I'm thinking, couldn't you convert any n-dimensional space to a hyperspace or hypersphere surface just by adding one dimension?
Well, yeah, so like topologically, right, a sphere with a hole is equivalent to a whatever n-1 dimensional space, but it's not true that math on the surface of the hypersphere is the same as linear algebra on Rn. So if you're going to do all of your math using linear algebra, then I think that you want to be living in Rn, not the equivalent n+1 hypersphere surface.
Yeah, it also means
since I don't know what n is, I'm not sure how important whether it's n or n+1. But
yeah, n is big, right? I mean, it was 512 in the transformer, but it's way bigger than that in all the models going on nowadays, right? And
Yeah.
rack systems multiply by 10 or something like that. So it's huge. Yeah, so sacrificing one dimension shouldn't be a big deal. But maybe, you have to worry about trainability. It could be that the magnitude dimension is easier to train in certain situations
Yeah.
than crawling along, an arc. And it also sort of brings up the idea of, constraining your adaptations to be rotation matrices. So instead of just fully general MLPs, why not just have rotations in, arbitrary directions, and that way you can't get off the sphere. So I don't know how well that might work out, but all these things can be very appealing, but you really just got to stop and look at the what you're doing to the loss function. Gotta visualize the loss surface, and you want to see it look more like a smooth bowl, not less like a smooth bowl. And that's the key to all this stuff. Don't start throwing nonlinearities around willy-nilly. That's the lesson of nonlinear optimization before machine learning. Then machine learning came along and said, well, due to the blessing of dimensionality, there's so many ways down, we get away with it anyway, even though, there are no guarantees. We get away with it all the time on the scale of trillions of dimensions. Weights, I should say, not dimensions.
Julius, one other question to distract us here. I'm curious because that prior architecture that you showed us had, what was it, pitch, volume, and then something else you said. And I'm wondering if that's something else then, yeah, the Z, does the Z space fall into this unit sphere then?
I would put it on the unit sphere. Yeah, I really would, because if any modern network here, although actually it might be kind of CNN style. You know what? I'm just going to go ahead and bring up, you'll get to see my system here. So this is a network directory, and I'm just going to open DDSP anything.pdf, and here's all my papers beginning with DDSP. Unfortunately, it's way more than I expected. So let me find the right one. So it's got Jesse Engel as the first author. And see, I need my RAG system. I can figure it out from the file name. DDSP dash original. How about that? Original at iClear. So here it is. And oh, that's not, I'm trying to make it full screen. Didn't happen, but this is okay. So here's that diagram we just had, right? I want to find the diagram of the architecture. Here we go. So the encoder goes into MFCC, mel frequency Kestrel coefficients. I think of that as the time domain representation of a smooth log power spectrum, which is very audio friendly. So you see mel spectrograms all the time. It's basically it's an audio. It's a dB spectrum over a quasi psychoacoustic frequency axis called the mel frequency axis, which is not as good as like the bark frequency axis, which is not even as good as the equivalent rectangular bandwidth. So it's kind of a crude perceptual audio axis, but it's better than linear. And then you logify it to make it more like dB, and then you smooth it so that you're just looking for timbre. So you're trying to, you don't want any spectral lines or anything in there. You want to catch all the resonances and so on. And then you go back to the time domain and you truncate it to get the smoothing done. So that's like, they call that liftering. It's the dual of filtering. That's the whole Kestrel world there. And that was initiated primarily by Ron Schaefer, who's at Stanford. I just saw him the other day. He's still teaching. 1975, his book came out, Oppenheim and Schaefer. That was a really big foundational book in digital signal processing. But this is just very, very popular encoding for audio, for, timbre, audio spectral envelopes, let's say. So you normalize, then you go to a gated recurrent unit. And so, as most of you, I'm sure, know, that's kind of the successor to the LSTM. And it's sort of the precursor to, Mamba and the SSMs, state space models of today. But you could say that we're going back to this, or you could say that what we're doing now is just really getting this right, getting gated recurrent units to do a really good job. And so then there's a final dense layer, and out comes your timbre vector. And then for decoding, you take your timbre vector and you now bring in your pitch from the CRAPE pitch estimator and your loudness, and they each go through MLP. So the the purpose, I mean, you just know this, right? But if you want to transform it, if you want to do interesting transformations, then you give it its own multi-layer perceptron. And so you do that individually for the pitch, the timbre vector, and the loudness, and you concatenate them together and go into another gated recurrent unit, and you get a bunch of channels out that are concatenated, and then you go through multi-layer perceptron, then dense for harmonic envelopes. These are amplitude envelopes for additive synthesis, sinusoidal components, and then you have your filter parameters for the noise, the filtered noise component. So, you know, in all of these, I'm sure, you know, a modern implementation, well, let's just say I would bet heavily that a modern implementation of these things would use RMS norm liberally, you know, between blocks and sometimes even between sublayers. You know, you see RMS norm like at the output of the attention layer before you go into your pointwise MLPs, and and you have another RMS norm after the MLPs. So it looks like people want to be on that sphere. And so I would put this on the sphere myself. That's kind of a long way to answer that, but I got to bring up these figures. That's what. This is the original paper. I cleared 2020. I thought that stuff went back earlier. I think the first thing was 2017. Even 2016, I think something started there. So okay. So any more questions, discussion? Where did my presentation go here? Oh, I see. I'm in. Let me kill out of this one. So my presentation is just one of these mini PDFs. I'll get here this way.
I want to respond to Ted's comment in the chat. If yeah, I'm sure that the vector magnitude is meaningful, but with 500 or 1500 dimensions, didn't we establish that almost any two directions are orthogonal, or mostly orthogonal in those high dimensional spaces? So I'm really curious to know what happens with this experiment. But anyway, thank you, both of you.
Yeah. So I think briefly when you're talking about those neural network layers, what you're really trying to capture is activations, but not necessarily a metric space. So what I'm saying is if you want a metric space, it's a vector space, and then you are going to have magnitude as a separate concept from just simply do I activate or do I not? So if you have like a vertical line detector, you don't really care about the magnitude, because you want it to be just kind of on and off. And then if you compose those to make a triangle detector, then it's kind of on off. So I think RMS norm liberally there works really well, and then it keeps your gradients and your training processes kind of within, you know, well-contained ranges, so you don't get underflow, overflow, all that kind of stuff. But eventually, if you're going to do something other than just classification or whatever, then at some point you need to be living in a metric space, is the way I feel. That'd be my high-level summary.
That makes sense. Yeah, they're really two distinct functions. You know, one is like you've got the equivalent of logits where they're just on or off, and you just and then you also have the issue of training ability. There's only one learning rate, right? Like 0.01 or something, and the learning rate multiplies the gradient, and the gradient's in units of the data. And so if the data is not normalized, then the learning rate has a different meaning along different components. So just purely from a normalization of the gradient step size point of view, you want to be doing something like that. So you actually have multiple independent reasons to want to be normalizing. Yeah. Oh yeah. One thing I want to really stress is that this thought experiment that I'm doing here is in no way intended to be complete. This is really just an idea that gives you one motivated derivation. In other words, it's one way to get to the mechanisms that you find going on. So it's but it's, you know, I really should emphasize that it's one of several, and I've identified a few others myself. And so we just talked about 3 different motivations for RMS norm. And so there's a lot going on here. And in the vector memory, there's more than that, right? So, you could just carry this further and say that, well, so transformers are just looking for vectors in a vector memory and adding them up to get new vectors that mean something new, or that, contextualize a vector and all that kind of stuff. And you might be tempted to think that's all that's going on, but it's not, right? And we know from a few weeks ago that there are things like attention sinks that go on in there. So, and there's induction heads, and who knows what all is going on in there. And I don't even know what all is known, and what all is known is almost surely incomplete, right? So, but that's the fun we're having, is we're just trying to figure out ways to motivate, something that might be going on, and then we can make simple experiments and test it out, and that's the iteration we're on, I think. So yeah, let's have a lot of that kind of discussion, because I want to learn more reasons to do these sorts of things. The more insight you have, the better, right? Okay, so where was I? Stop me anytime. There's a new message in chat. Syllable stress is sort of oh, that's done?
Julius, I've been going off onto something that we can get to later. I don't want to interrupt you with. So I actually work on this pronunciation assessment for language learning intelligibility remediation since 2015, and using confidence scores from speech to text since last November, when I read the 2002 paper that says it's okay to do that, when all of the past was about trying to avoid doing that, because you can look up the history of goodness of pronunciation going all the way back to 1989. But I did make some comments on there that I hope we can read later, and I hope whoever is saving the recording can save those in chat. I have a few more comments I want to make, but I don't want to interrupt you on them. We'll get them if you get to the end of your slides. I'll bring them up then.
Okay, we'll remember for discussion. All right. Yeah, well, stop me anytime, especially if you want to add stuff, or you want to, ask something that's not clear. Okay, so we made it to RMS, or at least one motivation for RMS norm, but it also motivates normalizing embeddings to the hypersphere, which, as far as I can tell, is not the normal practice. And either there's no good reason to do it, or maybe it's a good thing to do, and we're gonna have to show that. So that's exciting. So I'm gonna have to do that experiment. It's not hard, just project onto the sphere during training, and you kind of force it to crawl along the surface is the only thing it can do. Okay, so I just threw together a quick derivation, because I don't know if everybody knows this. This is an example of the kind of stuff that I'm missing a space here. This is the kind of stuff that I learned in school as a graduate student. So you have two random vectors. Let's say the coordinates are normally identically distributed Gaussian random variables, and let's say they're unit norm. So you take a dot product, and here's their components. And so here's the dot product written out, the inner product. When I say dot product, I mean inner product. Those mean the same thing. And then if we square that, we get this. And now if you take the expected value, which just means average it over a bunch of random vector selections, then the expectation operator, or averaging operator, goes inside the sums. And because of independence, you get the expectation of the product is the product of the expectations of the independent variables. And so then you're just left with this. And because these are white noise, it is only something when I equals J, and therefore it's just the variance of the process, and that's 1 over n. So this just becomes 1 over n squared, and then you sum that n times, and you get 1 over n. So this is just a derivation that maybe you haven't all seen, because I think it's from the signal processing field, statistical signal processing, that derives the expected inner product of two random vectors in n dimensions. And so it shows you what it should, what it is. And so it actually suggests where you should set your initial biases, right? If all your vectors are randomly, have random coordinates on a unit sphere, then your bias to not detect those should be greater than 1 over n. So that's an interesting little thing. But again, if n is huge, that's close enough to 0, just make it 0. I don't know. Or make it 0.01, and then you're way above what you need, and nothing fires until it's got something interesting going on. So, this is just, to me, pointing out, you know, the kinds of things you can get from this kind of analysis. So there's just what I just said. So yeah, initialized bias is larger than 1/n. Also, you know, when you add vectors, it suggests, let's say you add m vectors together, like you're doing attention or something like that. It suggests that you divide them by square root of m, because that would be power normalized. So that keeps them on the sphere sort of on, you know, to first approximation. You could say it's more RMS norm preserving. And you see this in architectures. You know, they actually, you know, will do the power normalizing sums. And they also did a power normalizing scaling for the SSM feedback component, you know, relative to Mamba. So one of the main differences between Hawk and Griffin relative to Mamba was this power normalizing gain going into the expanded state. That's just a little by the way point. So I think they're thinking that way. I think at Google DeepMind, they're thinking like this, seems like. Okay, so so the idea is just stay near the Unisphere. But anytime if you're going to get into an RMS norm pretty soon, then don't worry about it. It'll happen there anyway, so you don't have to bother with it. And so this is the idea we just talked about of applying RMS norm during training for your vocabulary embedding, and just, you know, start on the sphere and try to stay on the sphere. It's just kind of a suggestion based on the way we're thinking right now, which is only one of many ways of thinking. And who knows how many more ways of thinking are going on, you know, potentially. So, oh, here's another suggestion. It says that, so, you know, if you look at the model dimensions as a function of size, I actually have that data on my next slide. You see that the dimension does go up with the size of the network, but based on our way of thinking right now, it should really just be a function of the layer width. And it might as well just change. In other words, your vocabulary size determines how many patches you need on the hypersphere to, you know, space them out. Okay. And so, so your vocabulary size, you know, it's how many classification classes you have. It tells you how much you need a dimension large enough to accommodate that. And then when you go through, let's say, a transformer layer, how many symbols are needed there? You know, how many classification patches are needed there? How many vector domains do you need? Well, then your model dimension really only needs to be big enough to accommodate that. So it seems like we should be scaling our model dimension as a function of layer width as we go through the network. That's just, you know, kind of it just follows from this way of looking at things. And so I got interested, and yeah.
I have a quick question, and maybe it's for Ted. When you look at transformers, the residual streams carry more than just the embedding. It's carrying additional information. So kind of that model width has to have sufficient representation. And I guess I'm trying to correlate that to what you're saying here. Is it's not just your vocabulary. It seems like it's more.
As you go through the layers, yeah.
Yeah.
Yeah. So what, like, especially if you look at the transformer circuits work that Anthropic is doing, what you see is that powerful LLMs like Claude 3, GPT-4, they are representing in the millions of different concepts. And for us, it's just not particularly compute efficient to set your model dimension that high. But what they're able to do, because these signals are very, very sparse, essentially, if you're familiar with compressed sensing, they're doing compressed sensing on these sparse signals living in this residual stream. So it would actually probably train faster if you gave it a 16 million dimensional residual stream, but because they don't have that, then they have to learn how to do these I don't know how to say this over complete basis of signals sharing with each other, but because they're sparse, then the interference is relatively low. That probably means something in signals world for you, Julius. I'm just sort of barely scraping by.
I've seen some of that. They call it superposition, where a feature will participate in. It'll actually be an overlay of many features, and so I see it as like you think of logits, right? Only one logit counts, right? And when I first started working on this stuff, I didn't think in those terms. I wanted to output, let's say, an integer, right? And integers are more like these superposition of features where you're encoding, right? So you're using a series of a set of logits to make, let's say, an int, as opposed to having a separate logit for every int. And so it seems like it's that kind of encoding that they're calling superposition. And one of their big mechanistic interpretability techniques is to up project to a gigantic space where that doesn't have to happen, so that they start to get, if the neural net can have a separate logit for every classification cell, it will do that apparently. They don't have to, pile up into an encoded group. So that's apparently a big thing there.
That's really interesting. That might answer a question I was going to ask Ted is, how do you know there's millions of dimensions?
Yeah, so the paper that Jim just put in the chat, I believe the medium-sized Claude 3 Sonnet is believed to have a residual stream around 16,000 or something around there. And they believe that with their large run, they blew it up to a 34 million dimensional space, but a lot of it ended up being empty, about 2/3 of it. But so they still found over 11 million interpretable concepts living in this residual stream. And in their article, it says that you can have, I don't know this math. Okay, I'm just repeating what I read, that if the residual stream is 512, you can have e to the 512 power almost orthogonal directions. Okay, you can clearly only have exactly 512 perfectly orthogonal directions, but the number of almost orthogonal directions grows exponentially with n.
Oh, interesting.
And so you end up having the ability to pack a whole lot of information in there, but it requires high sparsity. So,
and when you say high sparsity, I assume you're talking like in a temporal dimension.
Yeah, so in other words, the features cannot be present at the same time.
Yeah. That's what I thought.
So my counterexample is if you were doing house pricing, okay, estimating the cost of a house, if you had like square footage and number of bedrooms, you cannot encode those using compressed sensing because every house has a value for number of bedrooms. Right? But hypothetically, if you had 11 million extremely rare features, okay, has a Rodin sculpture in the backyard, has a view of the Eiffel Tower, whatever. They're so rare that the fact that those directions are not completely orthogonal, the odds of you getting interference is really low. Now, in the case where you do actually have a Rodin sculpture and a view of the Eiffel Tower, then if you imagine like two directions that are like this, when you sum them, you just get the point in the middle. And so you might actually interpret that as neither the sculpture nor the Eiffel Tower, but instead you'll read it as has a view of the Empire State Building. And you'll just get completely destructive interference and completely mess up your model. So if that's rare enough, if it's sparse enough, then your loss will be very low, even though this happens 1 in a million times. But what you gain from the expressivity of having all of these million features will outweigh the occasional interference. But when you have very dense features, the interference is going to happen all the time, and you're better off just saying, I won't even create a feature for has a Rodin sculpture in the backyard, because getting high fidelity on my dense features is more important than expressing this thing that happens so infrequent. Does that make sense?
That's very interesting. That sounds like could be a fun paper to review.
Yeah, and actually, in a different meetup, I just did this. I have a slide deck which is the walking through the concepts in terms of linear representation hypothesis and this polysemanticity, this overcomplete basis, and how you manage to cram more features than you have dimensions. Because in 2 dimensions you should really only be able to express 2 things. You can express both positive and negative, but you can only express 2 things. Yeah. And they actually did in the toy models paper, they actually tried training it on 5 things. And when the 5 things were very dense, it would take the 2 most important ones and represent those and throw away the other 3. And when they got to 90% sparsity, and I don't know the exact definition of 90%, but when they got it to like 90% sparsity, then it actually represented them in a pentagon as 5 different directions. And none of them are perfectly orthogonal to any of the others, but the interference was just rare enough that they gained more from keeping around all 5 concepts than they lost from the interference that occasionally popped up.
Also, you don't need exact orthogonality. You can be just 30 degrees and consider that to be orthogonal enough. In other words, you can orthogonalize with subsequent processing if there's any separation at all that's resolvable. This is something.
Yes.
This is something that we do a lot in sinusoidal peak analysis. So you can have overlapping peaks, and it's a question: can you resolve them? But you have to start making modeling assumptions. You have to assume that it's just there's only those 2, and if you can under that assumption, you know exactly how to take them apart. So it's not robust anymore.
Yeah, that's cool. Yeah. So if you knew that like you're never more than like 30 degrees away from orthogonality, then that means that anything less than 1/2 you just kind of throw away.
Yeah.
Right. Anything more than
It's the
1/2
threshold. Yeah.
you read out. Right. But again, that doesn't solve the problem of if you have 2 vectors, then they can add to something that then whatever that is, like the destructive interference, where basically what you're left with is not the sum of the original 2. It looks like something completely different. Then when you try and read it out, because they're canceling each other, you're not actually just getting half of one or 0.7 of one or whatever. You're actually getting a completely different signal that's somewhere in between the 2 of them.
And that happens in sinusoidal peak estimation as well. It just collapses into one lump somewhere in the middle, weighted by power. Yeah, no free lunch. But under the right modeling assumptions, you can extend it way beyond just orthogonal. I had ChatGPT generate this table. I don't know why Claude's not on here. This is just what it generated, and I didn't check it, by the way. I just thought I got it.
They've never disclosed Claude, so it won't be on there.
Oh, okay.
We have guesses, but it's not public.
Okay. So this just gives you a feeling for the model dimensions in the various models, and you can see that there's a wide range. There's also, very surprising uniformity in the vocabulary sizes. Like it's basically just either 30K or 50K. That really surprised me. I didn't know that. 32K is over here. And then on the next slide, I had ChatGPT make a Python program to plot it, and did a good job with that. So here's the original transformer down here, 512 model dimension, 65 million weights, I believe, roughly, and then the 30K vocabulary size. And it's interesting that they tend to fall on this line. This is a log line, and I'm also very interested that Albert is such an outlier. There's a whole line of Alberts, that's the light Bert case where it was trained just to be, starved for parameters, but they kept the model dimension the same. It might have been a distillation. I don't remember actually. So it might have, had a reason to keep the original model dimension and just, lighten it up on the weights. But it's a very nice parallel line. But the others are a pretty nice pack. T5 is also interesting that all the various T5s tend to be right here. We like 1024 for our model dimension, and we'll have all the different sizes there. So I thought that was informative to look at. And let's see, did we finish up over here? Yeah, just some suggestions. So architectures. So we got this memory, this vector memory. This is Midjourney's work here. I said, give me a glass sphere with vectors, unit vectors protruding from the origin to the surface, and it somehow always wants to pierce the surface. So it's in need of a little RMS norm here. So your input vectors come in, and you go through your delay line. So this is a vector of unit delays in the model dimension, and they just add up, and that's your vector memory. And life is good. We can find any vector that ever happened for all time by just doing a dot product. Given a sufficiently large model space, and given that the vectors are separated well enough in that model space, we can put a perceptron here and take a dot product of this one. I guess I would call it a pointwise perceptron, pointwise dot product in the model dimension to detect any vector that ever happened here, if they're separated well enough. So that suggests, well, maybe we don't want to just add up all vectors for all time. Maybe once in a while we'd like to reset our memory. So, for example, maybe we're doing a sentence embedder, and we would like to maybe just clear the memory after processing a period, unless it's part of a number or something like that. So you have some end of sentence detector that can be another neural net that was trained somewhere else. I'm sure there is one, sentence segment or whatever, and then you use that to fire the reset. So in the architecture we're working with, you would just set the feedback gain to 0 for one step, and that would clear the memory. And another thing we might want is suppressing unimportant inputs. Why use up a vector on the sphere if it's just the word or some other completely just extraneous noises, extraneous typographic formatting and stuff, ads, I don't know what, just anything extraneous. We can have an extraneous input detector that drives this one. And so we set the input gain to 0 for unimportant inputs. So that's basically gating, and of course it's extensively used. It was what made Mamba a big step forward over S4, S5, S6. I guess it is S6, right? So you have extensive gating, and yeah, I guess it starts with the LSTM in the 90s, and then gated recurrent unit, of course, is doing it. So it's a big thing. Got to do it, and it's very important. Can't get away from it. And so this is just a way of motivating it. And now we have that. And so now we need another idea to, this is all 2020 hindsight invention, right? What do we have to invent to get what's happening? So now let's think about learning these gains as a function of the input. So we can classify the input. If it's unimportant, we set the gain to 0 or make it small. And so we're gonna have training data, input and output data, and this is of course what people do. So you have a learned gate, and you have a learned feedback coefficient, and that's a form of gated recurrent unit. And so this motivates some ideas. Instead of just learned gains, why not make them activations? Because we're thinking of them as gates, and that's what you did find in LSTM and gated recurrent unit. But in Mamba, it came out kind of differently for the feedback. And so that's a very interesting fine point. In other words, if you just do this learn gate as an activation, it can give you training problems. That's what leads to things like vanishing and exploding gradients. So you also have to have some intuition about this feedback loop and how to make it, be robust. And so in Mamba, it introduced the idea of actually, I think it came along a little bit before that. I think it started with um, um, S4D maybe. Anyway, but the basic idea is you want to learn it not as a parameter itself, but as an e to the minus parameter, where that parameter is made positive. So delta is soft plus of some parameter. So your parameter is here, and it's training as a function of input and output, and it can go anywhere. It can do anything it wants. It's just any real number. But then we run it through soft plus. Now it's going to be positive, and then we have e to the minus that, which can be approximated as I minus I delta if delta is small. And the idea here is to structurally enforce that it be in a good range. And we can also keep delta greater than 0. And this is very much prominent in Mamba, for example, and all the SSMs that train well, right? They sometimes call it linear gating because this all looks linear, but it's not, because it's, it is ultimately a function of the input data. But if you disregard that one, then it looks linear compared to, let's say, an activation, right? So there's no activation here. This pole is learned as e to the minus soft plus of parameter. And that's the kind of thing we've been doing since the 80s in system identification for audio, which is, minimize the error that you really care about. In other words, in a recursive feedback loop, which we've been, optimizing since the 80s, be careful with those poles, those feedback loops. Make sure they're bracketed. They can't go greater than 1 in magnitude. Initialize them carefully. I think it was the Mamba paper that pointed out that if you just randomly initialize the feedback matrix, then you get 50% on MNIST. It's just terrible. But if you initialize it carefully, you can get state-of-the-art performance. And so the rule of thumb to just randomly initialize your parameters doesn't pertain here. This is not where you do random initialization. And you also have this structural transformation. And it's also significant that you're actually optimizing the log, because that's much more what you care about. It's the log that is proportional to, let's say, decay time. So if you think about your memory duration, then that's more in the exponent here. So it's just getting in the right units. And what I always think of, in the audio world is I want to minimize perceptual error to the extent that I can. What is the loss function should be as perceptual as possible. It's what you really care about. And the translation of that loss into structure has to be robust and always stable. And so when you do that, you don't get vanishing and exploding gradients. And so when you think of how long, LSTMs and gated recurrent units were suffering from that problem, and then it's cleared up by this, basically. There might be more to it than that, but as far as I can tell, that's basically it. Then, this kind of signal processing thinking is valuable and maybe could have saved us some time. Maybe could have been doing a lot better LSTMs in the 90s even. But it's hindsight is always so clear and easy, right? But I would totally sympathize that we're thinking in terms of activations. We're thinking of a reset button for the feedback. We're just trying to, set it to 0 whenever we need to clear it, and the input we set it to 0 when it's unimportant coming in. So you gotta. So you probably want to use activations when you can, but in a feedback, you got to be really careful. It's very sensitive. I just realized it's 8 o'clock. Do I need to suddenly stop? Is that where we are?
Probably, is this a good stopping point? Let me ask you that.
Well, let me look. Yeah, I can pick up here next term. So let me just briefly scan the future here, and we can pick up next week if you want. So the next invention is skip connections by just introducing an output gate, and then we're going to vectorize one more level and get to state expansion in structured state space models, and then we make it all the way to attention. And so there's an argument. You can kind of derive everything if you have to.
Cool. Yeah, this looks like a decent spot to stop then, Julian, if that's okay with you.
Yeah, we can stop with the gated recurrent unit.
Okay, we shall do that then.
Could I I ask a favor? Before we stop, could you preview the remainder of the talk? Because I'm fascinated. I can stay here for 45 minutes after you turn off the recording. And I just, I want to offer the ability to answer questions about the stuff I typed into chat. But I also love to see a preview of what is remaining here, because I love this talk.
Thank you. Well, it sounds like you've, well, I think for signal processing people, it's like, it feels good, right? It's like things are in the right language. You know, the
Terminology is
matrices are
correct.
transposed right. Yeah. Well, thank you very much. I appreciate it. So the preview is, we're going to do vector detection in parallel. We're going to do sequence modeling, which motivates positional encoding. We're going to avoid amplitude decay, which everybody uses. So in other words, from a signal processing point of view, we want to reserve the amplitude dimension for similarity scoring, and we're not going to use that. But we're okay with sinusoidal amplitude modulation as used in the original transformer. And we're okay with rotating in the space, which is now the big thing, rope, rotational positional encoding. So I feel like that's very strongly motivated. And then we're going to go beyond the one pole to an FIR filter, and transformer is going to fall out of that. And this is also an extension of the SSM if you just have a state expansion factor that is large enough. So your state expansion factor becomes your context window length. So this is kind of wild. This is not the way people are thinking about it. But it is very natural, falls out very simply and nicely. And it's equivalent to just, a standalone context buffer with an FIR filter on top. But, to really get to the transformer, you have to add relevance gating. You have to say we want to create new embedding vectors as sum of existing embedding vectors. And we're going to measure relevance using an inner product, which I would say is very, very natural. And so you get right away to the query matrix. And you can sort of argue for the key matrix as well. But I would say to really get there, you want to get the idea of multi-head attention, because then you need down projections. You need down projections from the input to the query space, the key space, and the value space. And so once you're doing that, then all the other ideas for why you might want a key in place of just using the vector, just to sort of drive this one point home, why don't you just have this for your attention, right? So your vector, you're looking for a relevance of a vector, so you multiply by the vector, and then you just add the vector. I mean, why would you want anything more than that? So in other words, the way we're thinking was to say that this is the attention calculation, but that's not what they do. They have this, query key and value generalization of it. And there are a lot of reasons, and it'd be a lot of fun to talk about next week, what might be happening there. And of course, the answer is to train it up and see what it's doing. And the net will tell us about that. So and this is my last slide. So this is my mid-journey finale right here. I don't know.
And Julius,
Yeah.
you were worried this was only a 15-minute talk?
It started out that way. It did. It did. And I'm going to put this on my webpage. So, if you search on my name, Julius Smith, you'll find my homepage, and look at the bottom for videos. And I'll have these slides sitting there tonight. I'll put it there. And,
Thank you, sir.
GitHub repo. So you can also go back to the Karma Open House version, which is, that was supposed to be 15 minutes as well, but I always have too much stuff. It's just standard. And I don't have to go, so we can hang out for a while.
That's okay. I just want to, I know certain people are starting to drop out here, and I think
Sure.
it'd be best to do that, if that's okay with you, to stop at least the
Yeah,
recording portion of this.
We can
No
pick it up
problem.
next week.